When light scatters off a molecule in the air, you picture a collision, a photon, a little packet of energy, streaking through space until it strikes an atom. The atom deflects it. The photon careens off in a new direction, its momentum altered, like a marble hitting the edge of a glass. This is the image in your head. It might even be the image your textbook gave you. It's wrong. Not wrong in the sense that it gives bad predictions. Wrong in the sense that it describes a process that does not occur. There is no impact. There is no ricochet. The photon does not glance off the electron's surface because the electron has no surface. It does not bounce because bouncing requires two objects to remain intact through contact. And that is not what happens here. What happens is this. The photon is absorbed. It ceases to exist. Its energy is transferred to the electron, and the electron, now oscillating, now accelerating, emits a new photon. That new photon is what you detect. That new photon is what you call scattered light. The light that comes out is not the light that went in. Scattering is not a deflection. It is a destruction and a creation. And this is not a technicality. This is not physicists splitting hairs over terminology. This changes the entire character of the phenomenon. Because if the photon is absorbed, then for some fleeting moment, it does not exist. The energy is held in the electron's motion. The electromagnetic field of the original wave drives the charge, and the charge, because accelerating charges radiate, sends out a new wave. That new wave has the same frequency, usually the same energy, often a different direction. But it is new. Feynman understood this. He understood that what we casually call scattering is actually forced emission. The incoming light does not bounce. It shakes the electron. The electron, in response, becomes a source, a tiny antenna, a secondary emitter. And once you see it this way, everything becomes strange. Because if scattering is emission, then the air is not a passive medium that nudges light around. The air is a volume filled with trillions of tiny oscillators, all driven by the same passing wave, all emitting their own light in response. The sky is not blue because blue light bounces more. The sky is blue because electrons emit blue more efficiently than red. Forget quantum mechanics for a moment. Forget photons, wave functions, energy levels. Strip it down to something older, something classical. An electron bound to an atom is like a mass on a spring. It sits in equilibrium, held by the electromagnetic attraction to the nucleus. If you displace it, it experiences a restoring force. It wants to return to center. And if you shake it, if you apply an oscillating force, it oscillates in response. This is not a metaphor. This is how matter responds to light at the most fundamental level. When an electromagnetic wave passes through space, it carries an oscillating electric field. That field exerts a force on any charged particle in its path. The electron feels that force. It accelerates, back and forth, driven by the wave. And here is the key. An accelerating charge radiates. This is one of the iron laws of electromagnetism. If a charge accelerates, it must emit an electromagnetic wave. There is no exception, no loophole. Acceleration and radiation are linked by Maxwell's equations as tightly as mass, and gravity are linked by Einstein's. So the electron, driven into oscillation by the incoming light, becomes a source of light itself. It emits, not because it wants to, not because of some scattering cross-section you look up in a table. It emits because physics demands that accelerating charges radiate. The electron has no choice. Now here's what makes this dangerous. The frequency of the emitted light is the same as the frequency of the driving field. The electron oscillates at whatever frequency you shake it. If you drive it with blue light, it emits blue. If you drive it with red, it emits red. But the amplitude of the oscillation, the size of the motion, depends on how close the driving frequency is to the electron's natural frequency. If you drive the electron far from its resonance, it barely moves. It radiates weakly. If you drive it near resonance, it oscillates violently. It radiates intensely. This is forced oscillation. This is every physics student's nightmare problem in second-year mechanics, a damped harmonic oscillator driven by an external periodic force. And this is what scattering is, not a deflection, not a billiard ball event, a resonance phenomenon. The incoming light drives the electron into oscillation. The oscillating electron radiates. That radiation is what you measure. That radiation is what you call scattered light. Feynman saw this clearly. He saw that you don't need to invoke particle collisions to explain why light changes direction when it encounters matter. You only need charges and fields. You only need the fact that fields shake charges, and shaken charges make new fields. The electron is not a target. It's a transducer. It converts the energy of the incoming wave into mechanical motion, and then converts that motion back into electromagnetic radiation. And once you understand this, you realize that the electron doesn't just scatter in one direction. It scatters in all directions. Because a driven oscillator doesn't emit in a single beam. It radiates into a pattern, a dipole pattern, mostly perpendicular to the oscillation axis, but spreading out in all directions nonetheless. Every electron touched by the wave becomes a little spherical source, sending out ripples of light in every direction around it. And that is where things start to fall apart. You've been told why the sky is blue. Shorter wavelengths scatter more than longer wavelengths. Blue light scatters more than red. So when sunlight enters the atmosphere, blue gets thrown around in all directions, and red passes through relatively undisturbed. This is called Rayleigh scattering. It's named after Lord Rayleigh, who worked out the mathematics in the 19th century. And the explanation you were given is not wrong. But it hides something. It hides the why. Why does blue scatter more than red? The usual answer is because blue has a shorter wavelength. Because the particles in the air are much smaller than the wavelength of visible light, and small particles preferentially scatter short wavelengths. But that just pushes the question back. Why do small particles scatter short wavelengths more effectively? The answer is buried in the oscillator picture. Remember, scattering is forced emission. The incoming electromagnetic wave drives the electron into oscillation. The electron radiates. The intensity of that radiation depends on how violently the electron oscillates. And here's the thing. The amplitude of oscillation depends on the acceleration imposed by the driving field. The electric field of a light wave oscillates sinusoidally. The force on the electron oscillates at the same frequency. The acceleration follows. But acceleration is the second derivative of position with respect to time. Higher frequency means more rapid oscillation. More rapid oscillation means larger acceleration for the same displacement. Larger acceleration means more intense radiation. The power radiated by an oscillating charge scales as the fourth power of the frequency. 4, not 2, not linear, fourth power. Double the frequency, go from red to blue, and the scattered intensity increases by a factor of 16. This is why the sky is blue. Not because blue bounces more, because blue shakes the electrons harder, and harder shaking means stronger emission. Rayleigh worked this out without ever invoking photons. He didn't need quantum mechanics. He didn't need particle collisions. He needed oscillators and radiation theory. Classical electromagnetism gave him everything. But even Rayleigh's explanation conceals something deeper. Because when you say the electron radiates, you're admitting that the scattered light is new light. It's not the original sunlight, deflected. It's secondary radiation, emitted by electrons that were driven into motion by the original sunlight. The blue photon you see when you look at the sky was not born in the sun. It was born in the atmosphere, in an oxygen molecule, in a nitrogen molecule, emitted by an electron that absorbed the energy of a solar photon and then released that energy as a new photon in a new direction. You are not seeing sunlight bouncing around. You are seeing the atmosphere glow. Every molecule touched by sunlight becomes a tiny blue lantern. The sky is not a passive reflector. It is an active emitter. A volume full of oscillating charges, all radiating in response to the driving wave, all contributing their own tiny piece of light to the diffuse blue dome above you. And if that makes you uncomfortable, it should. Because if scattering is emission, if the light you see is newly created, then what does it mean for light to pass through something? What is transparency? You think glass is transparent because light passes through it. You imagine the photons slipping between the atoms, threading through the empty space, traveling from one side to the other, essentially undisturbed. This is not what happens. Glass is not mostly empty space in any meaningful sense. The electromagnetic fields of the atoms extend throughout the material. Every photon that enters glass interacts with the electrons in the glass. Every single one. And if scattering is forced emission, if every electron touched by light absorbs and re-emits, then the light that exits the glass is not the light that entered. It's new light, emitted by electrons that were driven by the incoming wave. So why does the light emerge traveling in the same direction? Why doesn't it scatter in all directions, the way it does in the atmosphere? The answer is interference. Every electron in the glass responds to the incoming wave. Every electron oscillates. Every electron emits its own spherical wave, radiating in all directions. But these electrons are not randomly positioned. They are locked into a regular lattice, a crystal structure. And because they are regularly spaced, the light they emit has phase relationships. In most directions, the light emitted by one electron arrives at a distant point, slightly out of phase with the light emitted by another electron. The two waves interfere destructively. They cancel. In most directions, nothing survives. But in the forward direction, straight ahead, along the original path of the incoming beam, the waves from all the electrons arrive in phase. They interfere constructively. They add. The forward direction is the only direction that doesn't destroy itself, so the light doesn't pass through the glass. The light is reconstructed in the forward direction by the coherent interference of trillions of secondary emitters. Feynman was obsessed with this picture. He returned to it again and again in his lectures, in his books, in his explanations to students who thought they understood how light moves through matter. He wanted people to see that transparency is not the absence of interaction. Transparency is the conspiracy of interactions that rebuild the wave in one direction and annihilate it in all others, and this has consequences. Because if the electrons are not perfectly ordered, if there are irregularities, defects, impurities, then the phase relationships break down. The destructive interference in the sideways directions is no longer perfect. Some light leaks out. This is why frosted glass scatters, why clouds are opaque, why milk is white. Not because the particles are blocking the light, because the emitters are no longer coherent. The electrons radiate in all directions, and the interference pattern that normally reconstructs the forward beam is disrupted. Scattering and transparency are not opposites. They are two outcomes of the same process, determined entirely by whether the secondary emitters cooperate or not. When they cooperate, you get transparency. The beam survives. When they don't, you get scattering. The beam dissolves into a spray of light in all directions, each direction built from the incoherent sum of emissions from countless oscillators. And this means something strange. It means that when you look through a window, you are not seeing the world directly. You are seeing the world reconstructed, destroyed and remade, atom by atom, electron by electron, from one side of the glass to the other. The light that reaches your eye was emitted by the glass itself. The glass did not transmit the light. The glass became the source. Feynman didn't just understand scattering as forced emission. He understood it as a sum over sources. When a beam of light passes through a material, you think of it as a single entity, a ray, a wave, a stream of photons moving together, one thing traveling forward. Feynman saw it differently. He saw every electron in the material responding to the incoming electromagnetic field, every single one. Not just the ones in the path of the beam, not just the ones at the surface. Every electron within reach of the field. And each of those electrons, driven into oscillation, becomes an independent emitter. Each one radiates its own spherical wave, its own electromagnetic disturbance, spreading outward in all directions at the speed of light. What you call the light beam is not a single object moving through space. It is the superposition, the sum of all those secondary waves, trillions of them, all overlapping, all interfering, adding here, canceling there, constructing and destructing according to their relative phases. This is Feynman's picture, and it is radical, because it means that at every point in space, the electromagnetic field is being built from contributions that come from everywhere, from every oscillating charge in the material. The field at any location is the sum of waves emitted by electrons in front of it, behind it, to the side, below, above. No electron is irrelevant. No electron sits idle. They all contribute. Now, most of those contributions cancel. The electrons far from the beam path emit waves that, by the time they reach the center of the beam, are out of phase with the waves from other electrons. Destructive interference wipes them out. But they were there. They participated. The cancellation is not evidence of absence. It's evidence of conspiracy. The electrons don't know they're supposed to cancel. They don't coordinate. They just emit. Physics does the rest. And in the forward direction, dead ahead, along the original trajectory, the contributions from all those electrons add constructively. The wave rebuilds itself, not because the original wave survived, because the new waves, emitted by electrons driven by the original wave, align perfectly in phase and reconstruct the forward propagation. This is how light moves through matter. It doesn't move. It is continuously destroyed and remade. Every femtosecond, the electromagnetic field drives electrons into oscillation. Those electrons radiate. The radiation builds a new field. That new field drives new oscillations. The process repeats. Light does not travel through glass the way a car travels through a tunnel. It travels the way a rumor travels through a crowd. Each person hears it, repeats it, and passes it on. The message propagates. But no single voice carries it from end to end. Feynman understood that if you take this picture seriously, you have to abandon the idea of the photon's path, because the path is not chosen by the photon. The path is the outcome of interference among all possible emissions from all possible sources. And this applies everywhere, not just in glass, not just in air. Everywhere light interacts with matter. When you see a red apple, You think the apple absorbed all colors except red and reflected red back to you. But what actually happened is this. Every electron in the surface of the apple was driven by the incoming white light. Electrons in certain molecules absorbed specific frequencies and dumped the energy into vibrations, into heat. Other electrons, driven by red light, oscillated and emitted red in all directions. The red you see is not light that bounced off. It's a light that was emitted by the apple. The apple became a red source. Every scattering event, every reflection, every transmission, all of them are sums over emitters. All of them are interference patterns. All of them are the collective result of countless charges, oscillating, radiating, building the field one contribution at a time. And if every direction is the sum of contributions from every electron, then why does the forward direction dominate? Oh, the question is not why light scatters. The question is why it ever goes straight. If every electron emits in all directions, if every electron contributes a spherical wave spreading outward into space, then why doesn't the beam dissolve immediately into chaos? Why does anything resembling a forward propagating wave survive? The answer is phase. Imagine two electrons, side by side, both driven by the same incoming wave. They oscillate in sync. They emit in sync. At any distant point, directly ahead of them, their emitted waves arrive at the same time, same phase. They add constructively. Now imagine a point off to the side. The wave from one electron has to travel slightly farther to reach that point than the wave from the other electron. It arrives slightly later, slightly out of phase. If the phase difference is small, they still add, just not perfectly. But now add a third electron, a fourth, a millionth, a trillion. Each one emits its own wave. Each wave travels a slightly different distance to reach that sideways point. Each arrives with a slightly different phase. And because the electrons are regularly spaced, because they form a lattice, those phase differences accumulate in a predictable way. For every electron whose wave arrives with phase 0, there is another electron whose wave arrives with phase pi. They cancel. For every contribution that adds, there is another that subtracts. In directions away from the forward beam, the sum is 0, not because nothing was emitted, because everything was emitted and it all destroyed itself. But in the forward direction, something different happens. In the forward direction, every electron is roughly the same distance from any point ahead. The waves all travel roughly the same path length. They arrive in phase. Not perfectly, there are small differences. But those differences are much smaller than the wavelength of light, and so the phases align closely enough that constructive interference dominates. The forward direction wins not because it's special. It wins because it's the only direction where the geometry doesn't enforce cancellation. Feynman called this the most beautiful thing in physics. The fact that the straight line propagation of light, the most obvious intuitive thing about light, is actually the least obvious when you look at the mechanism. Light doesn't go straight because that's the natural thing to do. Light goes straight because every other direction destroys itself. And this has a strange consequence. It means the path of light is not determined locally. The photon doesn't make a choice at each point about where to go next. The forward direction emerges globally from the collective interference of all the emitters in the material. Change one electron's position, just one, and you change the interference pattern everywhere. Not by much. One electron's contribution is negligible. But it contributes nonetheless. The field at any point is not the result of light traveling from point A to point B. It's the result of every charged particle in the material radiating, and all those radiations summing according to their phases. This is why the speed of light in a material is different from the speed of light in vacuum. Not because photons slow down, because the emitted waves from the electrons have a phase delay relative to the driving wave. That phase delay shifts the peaks and troughs of the total field. The effective wave looks like it's moving more slowly, but nothing actually slowed down. The waves from the electrons still travel at c. The vacuum fields still propagate at c. What changed is the interference pattern. The slower speed is an illusion constructed by the conspiracy of emitters. And if you try to track which photon is responsible for the field at a given point, you fail, because there is no which photon. There is only the field built by all the sources everywhere, all at once. Feynman knew this led somewhere uncomfortable. Because if the forward direction is the result of destructive interference everywhere else, and if every electron in the material participates in building that interference pattern, then the light doesn't propagate causally from point to point. It propagates as a solution to a global boundary value problem. And that breaks something in the way we think about cause and effect. You think light travels from A to B. You imagine it leaving the source, crossing the intervening space, arriving at the detector. A journey, a sequence. Cause, then effect. But if scattering is the sum over all emitters, if the field at every point is built from contributions that come from everywhere in the material, then the notion of a single path dissolves. The photon does not choose where to go. There is no moment-by-moment decision, no local trajectory. What you call the photon's path is a story you tell after the interference has already happened, after all the electrons have radiated, after all the waves have summed. The path is not the cause of the outcome. The path is a description of the outcome. Feynman took this seriously. He built an entire reformulation of quantum mechanics around it, his path integral formulation. In that picture, the photon does not take one path. It takes all paths, every possible route from source to detector, straight paths, curved paths, paths that loop backward in time and forward again, paths that zigzag through every atom in the material. Each path contributes a complex number, an amplitude, with a specific phase. You sum all those amplitudes, all of them, and the interference among those infinite contributions gives you the probability of detecting the photon at a given location. In most cases, the wildly curving paths cancel out. Their phases are random. They destroy each other. The paths that survive are the ones where neighboring paths have similar phases, where the interference is constructive. And in the classical limit, those paths are the ones that extremize the action, the ones that obey Fermat's principle. The straight lines, the reflected angles equal to incident angles. But those paths are not chosen by the photon. They are the paths that remain after everything else has canceled. This is not a metaphor. This is not a mathematical trick. Feynman argued that this is what actually happens. The photon, if you insist on calling it that, explores all possibilities. Physics computes the interference. What you see is the result, and this creates a discomfort that doesn't go away. Because if the photon explores all paths, then it's not localized. It doesn't have a trajectory. The classical image of a particle traveling through space is wrong at a level deeper than uncertainty or wave-particle duality. The photon is not a thing moving through space. It's a disturbance in the electromagnetic field. And that disturbance is the superposition of contributions from every source that could possibly emit it. When light scatters off a molecule in the air, the molecule doesn't deflect a pre-existing particle. It participates in a global field configuration. It adds its contribution to the sum. And the sum, integrated over all space, all sources, all paths, produces the pattern you observe. Causality, in the sense of this caused that, which caused this, breaks down. What remains is correlation, structure, interference. The universe doesn't compute the future from the past by stepping forward in time, event by event. It computes the field as a solution to a wave equation, a boundary value problem where every point is connected to every other point through the mathematical structure of the theory. Feynman knew this was disturbing. He knew it sounded like mysticism. He knew people would accuse him of abandoning realism. But he also knew the math worked. The predictions matched experiment to absurd precision. Quantum electrodynamics, the theory built on this picture of light and matter, is the most accurately tested theory in the history of science. And it tells you that scattering is not a collision. It tells you that light does not travel through matter. It tells you that what you see is the interference pattern of 1 trillion emitters, none of them special, all of them contributing, building the world one superposition at a time. This is what Feynman discovered about scattering, not a better formula. Not a correction to Rayleigh's calculation. A different way of seeing. A way that strips out the intuition of particles bouncing and replaces it with fields interfering. A way that makes transparency strange and forward propagation non-obvious. A way that turns every scattering event into a sum over all possible sources, all possible paths, all possible histories. You look at the sky, and you think you see sunlight scattered by air. What you actually see is the interference pattern of every electron in the atmosphere, oscillating, emitting, building the blue from 1 trillion tiny conspiracies of phase. The sky is not lit by deflection, it's lit by creation. And once you see it that way, you cannot unsee it.